Hi everybody. So we're going to start with section 6.5, and it's kind of a recap of what we did in 6.4, as well as what we did back in chapter 5 with factoring. First and foremost, once again, we're solving polynomials just like we used to solve equations. One of the ways is by factoring. My very first piece of advice is make sure that you put your equation in standard form, set it equal to 0. And then the second thing that you need to do, I'm going to take out a GCF. I noticed that all of these terms have a factor of a 4 in common, and all of them have at least an x to the third power. So if I take a 4x cubed out, then I'm left with just an x squared, and then just an x, and then it looks like a minus 6. And then here, what adds to be 1 and multiplies to be negative 6. So I know 2 and 3, and I think a positive 3 and a negative 2 would work. So if I have 4x cubed times x plus 3 and then x minus 2, if you recall, we needed to use our zero product property in order to get our solutions, right? So we're going to set each one of these factors equal to 0 and then solve for x. So I have 4x cubed equals 0. I have x plus 3 equals 0. And then I have x minus, sorry, that should be a minus, 2 equals 0, right? So if I have these three pieces, right, my solution here, I would have to divide by 4, and I'd get x cubed equals 0, the cube root. It's kind of like a square root, but what number cubed would give me 0? Well, either way, that's just 0. And then here I would subtract 3 to get x equals negative 3. And then this last one I would add 2 to get x equals 2. If you look at this next one, we're going to talk about, we have to put this in, we have to put this in standard form. So I'm going to subtract the 26x squared to the other side. So then I'm left with x to the fourth minus 26x squared plus 25. Now this is a trinomial, right? But the degree is 4 instead of 2. But if you think about it, really all I'm doing is saying, isn't x squared times x squared the same as x to the fourth? And we can still follow the same rule as what adds to be negative 26 but multiplies to be a positive 25? Well, that would be a negative 1 and negative 25. Negative 1, negative 25. So if we were to do that, I would have to solve this by saying x squared minus 1 equals 0, x squared minus 25 equals 0, right? And then I could get my solutions here. I would add 1 to both sides. And I'd get x squared equals 1. When I square root both sides of an equation, I get x is equal to plus or minus 1. And then here, I added 25. X equals plus or minus 5. I also could have done this by factoring it further and getting difference of squares. So I could have had like x plus 1 times x minus 1. That's the same thing as x squared minus 1. X plus 5, x minus 5. That's the same thing, right? Okay. So I want to go through one more example with you guys. And we're going to talk about, once again, a little bit more of a recap of what we were doing in the last few sections. But if we were doing something like x squared, or x to the fourth, minus 10x squared plus 25. Well, then I could actually factor this. So what adds to be negative 10 multiplies to be positive 25. Negative 5 and negative 5 would. I'd get x squared minus 5. And then I'd have 2 of those, right? So I would put a squared on the outside. Okay. If I were to solve this out, do you see how I'm going to get an x squared minus 5 times an x squared minus 5 equals 0? Do I really need to solve both? No. What I'm going to do is just set one of them equal to 0. I'd have to add 5 to both sides. And then square root both sides to get x equals plus or minus square root of 5. But you know, I would get each of these solutions twice, right? And the reason I'm getting each of these solutions twice is, remember, I had two of the same factor, right? And when I solved this, I'm going to get two of those same equation, or the same solutions twice, which means their multiplicity. So how many times do I see that answer? Is twice, right? The multiplicity is 2. So once again, if you have a factor that appears more than once, this creates a multiplicity. And the multiplicity is how many times do you see that root, right? So if you look at the original 2 questions, right, I had 3 different factors, which means here I only had the x equals 2 once, so the multiplicity was 1. Here I had this one once. But technically, if I have 3x cubes, right, I have 3 x equals 0s there, right? So this one actually has a multiplicity of 3. In this next question, I had a positive 1 and a negative 1, a positive 5 and a negative 5. All of these had a multiplicity of 1 because I only saw it once and they had a degree of 1, right? But here, do you see how we had 2 of the same factor? That means each of these answers, plus or minus root 5, have a multiplicity of 2. Okay? All right, moving on. When a real root has a multiplicity of 1, the graph of whatever y equals your function will cross the x-axis cleanly. It'll go straight through. When the real root has an even multiplicity, the graph of whatever your function is does not cross the x-axis, but bounces off of it. So you're going to see with the even roots, or the even multiplicities, right? So even multiplicities, this is an example right here. Do you see how it goes up and then it hits your x-axis but then bounces off? I like to think about it as like even degrees are kind of like quadratics, right? X squared. And that kind of looks like a parabola, right? It's hitting the x-axis at a parabola. Whenever you have a real root that has an odd multiplicity that's greater than 1, so 3, 5, 7, etc., right? The graph is going to do, it's called a snake, or a bend. The graph bends, or snakes, or swooshes. If you remember, if you had me in Algebra 1, I used to talk about my snake functions, where all my odd degrees. It kind of does a little snake through the x-axis. Okay, so if we're looking at the multiplicities of the other functions, all right, and we could sketch a rough graph, we don't have time for that, so we're just going to skip that. And then, actually, maybe we have time for one of them. Okay, so let's do the first one where we had the solutions of x equals 0, where your multiplicity was 3. And then you had x equals, what was it, -3 with a multiplicity of 1. And then you had x equals 2 with a multiplicity of 1. Right? So if we were to graph this, first and foremost, I graph all 3 of my x-intercepts, all of those solutions. I have -3, 0, and a +2. I usually read from left to right. Anytime you have an odd degree function, it will always look like a snake somehow, some way, so it needs to go opposite directions, right? Your ends need to go opposite directions. And since that leading coefficient, I'm going to go back here, right? The leading coefficient was a +4. That means that I will have a snake that ends up going up as we go to the right. So I know I'm going to have an arrow that goes up to the right, and I know it's going to go down as we go to the left. And think about this for a second. We said if we have a multiplicity of 1, it's just going to go straight through that x-intercept, right? And then we have x is equal to 0, and it has a multiplicity of 3, right? So remember, multiplicity of 1 is straight through. If we have a multiplicity of 3, that means it's going to do a bend or a snake through that point. So somehow we need to come back to the 0, and we're going to do a little snake through it, right? So you see how I'm kind of building a snake. And then somehow I need to come back up to this x is equal to 2, and I need to go straight through because its multiplicity is 1. Am I expecting you to be perfect about this? No. Does my graph look perfect? No. But I should see your 3 x-intercepts graphed, and I should see some sort of attempt at a straight, snake, straight. Right? Does that sort of make sense? So I'm hoping, once again, you have an odd degree function. That means your ends are always going opposite directions. If we were to look at the example number 3, where our solutions were plus or minus the square root of 5, and they each had a multiplicity of 2, which means it's going to bounce, right? But if you think about number 3, once again, that one was an even degree function. So it should either look like a U or a W. So I always think of even degree functions as sort of like quadratics or fancy quadratics. So fancy parabolas are just a normal parabola. So if you have even degree, they should end the same direction. And since your leading coefficient's positive, it should be happy opening up. But if we were to look, remember, I'm just going to plot the square root of 5 is somewhere between 2 and 3. So if I have negative root 5 and then positive root 5, I remember it's going to either look like a parabola or it's going to look like a W, right? But I do know the ends should both be opening up because this is a U-shaped graph, and it should be opening the same direction. Okay, so if I have, once again, my multiplicity of 2 means I bounce off. Somehow I need to come back down to this root again, so I'm going to have to come back down and then bounce back off, and then off I go. Am I expecting this to be perfect? No, but I'm expecting to see you graph your zeros and somehow at least say that they bounced. And you should know if it goes the same direction or opposite directions. Remember, odd is always opposite. All right, last thing that we need to talk about is your rational root theorem. It's a bit tricky. So you have a polynomial that has integer coefficients. Rational roots, remember rational means no square roots or anything. Rational means fractional. So here is our rule. You can come up with all rational roots of our function if we know if p is a factor of the constant term of p of x and q is a factor of the leading coefficient. So q is the leading coefficient and p is the constant. And we can find that ratio of p's to q's. We'll get back to the irrationals later. Okay? But once again, if we identify all the real roots of this, you need to know what's your p and what's your q. So remember, p is the factor of the constant, so what goes into negative 4, and q is your leading coefficient, which is 2. What are my factors of negative 4? Well, that would be negative 1 or 1, negative 2 and 2. We could also have negative 4 and a positive 4, right? Because negative 1 times this. So really, all we're doing is plus or minus 1 plus or minus 2, plus or minus 4, right? And this is how I'm going